Good evening, everyone. Thank you for joining us tonight. Welcome to the Avexia webinar series. Our topic for tonight is Introduction to Epigenetic Methylation and Advanced Biological Age Testing. My name is Christopher Chu. I am the Director of Marketing for Avexia Diagnostics and will be your host for this evening. Today, I have the distinct pleasure of being joined by our guest, Ryan Smith, Vice President of Business Development at TruDiagnostic, who will be our presenter for this webinar. Ryan Smith attended Transylvania University and graduated with a degree in biochemistry. After finishing all the educational curriculum and passing USMLE Step 1, he decided to leave and open a pharmacy in the United States that focused on peptide synthesis and formulations for pharmaceutical preparations. That pharmacy, Tailor-Made Compounding, became the fourth fastest growing company in healthcare in the US. During that time, Ryan invested in several businesses in the functional medicine space. Ryan exited Tailor-Made in late 2020. Since then, Ryan has opened many businesses, including TruDiagnostic, a company focusing on methylation array-based diagnostics for life extension and preventative health care. Before we begin, we'd just like to do a bit of housekeeping. We encourage participation. So if you have a question, you may submit your question in the questions field in the right-hand area of the interface. We will answer the submitted questions towards the end of the presentation. If your questions are not answered this evening, you will surely receive an answer by email within a day or two. Without further delay, I will now turn the webinar over to Ryan Smith.
Yeah, thank you, Chris, and thanks so much to the entire Avexia team for having us tonight. We're really excited to be here, and myself included on behalf of TruDiagnostic, to hopefully introduce a lot of people to this new concept of epigenetic methylation biomarkers, and particularly the best-in-class age biomarkers. And so really excited to lead you through that journey. Just before we get started, a little bit more about sort of our team. You heard a little bit about me, but TruDiagnostic is still a relatively young company. We've been going now a little over 2 years. And this is the sort of the in-house lab team that you would see at our CLIA certified facility in Lexington, Kentucky. But we have a bigger team that's even represented here. And really what we're trying to do as much as possible is to really lead the investigation into epigenetic methylation as a biomarker for health. And we'll talk a little bit more about that, but we do that in a lot of ways. A lot is through collaborative research. So we work with a ton of universities for that benchtop research and really culminate it in these epigenetic test kits, which we offer to physicians and other medical providers, which we'll talk a little bit more about today. And so if you haven't heard of us, hopefully we'll do business together in the future, and would love to talk more if anyone would like to reach out to us directly. But tonight, what we really want to do is introduce this topic of epigenetic aging. And although we sort of buried the lead here a little bit with the topic, I always try and open up with these slides, looking at the links between many of these diseases. Here you can see a wide variety of diseases, everything from arthritis to kidney disease to cancer to type 2 diabetes or immune decline or cognitive decline. And we sort of ask, what do all of these risk factors have as the #1 risk for each of these diseases? And to supplement that a little bit further, we even talk about what happened recently in 2020, looking at the top 3 causes of death. And if you can look at these, we've sort of grayed out the slide down there, which shows all the different risk factors for these diseases. But these are the top 3: heart disease, cancer, and COVID-19. And what is the #1 risk factor for all of these different conditions, the 3 major causes of death? As you probably know already from the topic of our conversation, it is definitively one thing, which is age, and by a large margin. Here you can see, for instance, even looking at heart disease, the effect that smoking and hypertension would have to the relative risk of death versus age, which is, a much, much bigger factor in why we develop these diseases. It's also affected to most chronic disease. Actually, age is the #1 risk factor for almost every chronic disease and death. And you might be thinking, this is, we can't really fix our age, so why are we talking about this? And hopefully we'll put that into a little bit of a different concept, at least today. But age plays a major impact in all of our risk factors for disease. It's why we don't see 30-year-olds or 20-year-olds coming sick with the same type of disease we see in much older age. There's a reason for that, and it's a biological reason. And it really leads to this idea and this concept, which has been growing in recent years, of age as a disease. And this is definitely something that we believe here at TruDiagnostic, is that age is definitively a disease. And we know this from obviously it being the #1 risk factor for almost every chronic disease. But in addition to that, we see this in for sort of a molecular basis. Most people are familiar with the 9 hallmarks, now probably a few more hallmarks of aging, things like cellular senescence or dysregulated proteomics, or from nutrient sensing cascades. But all of these culminate or are defined as aging, or this progressive loss of function as we age. And this is something that we hope to change, and something that we think we can actually treat by having an ultimate diagnostic for it. And we know this by sort of if everyone in the world were just to increase their life expectancy by 1 year, we would, here in the United States, we would save over $256 billion in healthcare spending. And that would equal over 8.8 trillion if we could do it for 10 plus years of life. And so this could have a major impact into how we treat disease. And we're going to talk about a concept particularly called biological aging. And so, for many, many years, we know they have known that age is the biggest risk factor for disease, but we also know that it's not perfect. And one of the ways that we know this is by comparing people in our lives, or our own lives, our own personal experience. So for instance, we probably all know someone in their 70s who probably looks like they're in their 50s, and vice versa. We probably know someone in their 50s who probably is aging poorly and looks a little bit older or functions a little bit older. And this difference is called phenotypic variation, how the phenotypes of people across many different age groups can all vary. And so we know that chronological age isn't really good at picking that up. However, this idea of biological age, where we can actually look at biomarkers within the body to tell us how well someone is aging and what that aging appearance is like, can be definitively better. And so that's really what we're trying to find here, is a different marker for age, something that is not necessarily tracked by the number of times the Earth goes around the sun, but something that is actually tracked by someone's individual body, which can then explain a lot of that phenotypic variation. While some people age well and other people don't as much. And so that concept is this idea of biological age, or how old your body is. And what we're here to talk about today is these diagnostics for biological age. And this has been something that has been sought after for a long, long time. Even in the 1920s, they were defining biological age as your chronological age plus 1 year for every pack per day you smoke. So really crude measurements of biologic age. But the search for these measurements has really always been going on, and really trying to be as precise as possible. And really in 1988, the American Federation for Aging Research formulated some criteria for these biomarkers. And the first criteria was that it must predict the rate of aging. So in other words, it should be able to tell exactly where a person is on their total lifespan, and it must be a better predictor of lifespan than chronological age. In addition to that, it must monitor a basic process that underlies the aging process, and it must not overlap with disease. We don't want to measure necessarily disease, we want to measure aging, or that dysfunction that is associated with age. And then it must be able to be repeated frequently without harming the person, such as a blood test. And it must be something that works in both humans and laboratory animals, so that we can do lab testing to validate this in humans. And really until 2013, there had been no such biomarker that had really emerged. And that really changed in 2013 with the advent of what we're going to be talking about today, which are these biological epigenetic clocks. And if there's one big takeaway, I think, from today, it is that epigenetic methylation is a biomarker that will impact every area of medicine. And here's a quote we always like to talk about from Silicon Valley MD, PhD, who says that 5 to 10 years from now, the health system that does not use epigenetic data to improve their medical delivery will be deemed archaic. And we certainly agree. Epigenetic methylation as a biomarker is impacting every area of medicine. Everything from liquid biopsy testing to see, if you have any type of cancer, to developing prognosis or predictive risk factors for what drugs you should take in cancer. This is applied to every area of medicine. And so there's really no area that won't be impacted from this over the course of the next 15 to 20 years. And many people actually anticipate it'll overtake blood testing in the next 20 years in terms of frequency, via all the different things that we can do with this measurement. But today we really want to talk about those epigenetic clocks, right? How we're using these markers, these epigenetic markers, to be able to tell you how your body is aging, and then tell you what that means in terms of your own risk, and then hopefully how we can use it to reverse that clock, how we can add years to your life and improve your health span by treating this as a primary outcome. And so before we get into those epigenetic clocks, I want to go back a little bit further to talk about what is epigenetics. And this is always something that's important to talk about with patients because most patients know what genetics are, but don't necessarily know what epigenetics are. And so the way that we typically explain this to patients is by talking a little bit about their point of reference, which is DNA. And we say, every cell in your body has the exact same DNA sequence. If we were to take your hair cells or saliva or your skin cells, all those cells have the exact same sequence of DNA, which is unique to you as an individual. But we also know that those cells behave vastly differently. The cells in your mouth behave differently than the ones on your skin, and those behave differently than the ones you would find in your heart or blood. And so, how do these cells act so differently if they have the same underlying instructions? And the way that we answer that is by talking about these epigenetics, or sort of stands above for the DNA, and these are how these genes are regulated. Basically the on or off switches for all of that gene expression, which can lead to essentially how your cells behave and affect your biology. And so that's what we're looking at here are these epigenetic mechanisms which regulate gene expression. And so there are a lot of different epigenetic methylation, or I should say epigenetic markers, which can handle gene expression. These are probably the three most common, but really what we're looking at today is only DNA methylation. And so DNA methylation is essentially just a small chemical tag of a carbon group onto the DNA. And what it does whenever it attaches is silences gene transcription. So essentially this is the DNA off switch, how we regulate all that activity off. In comparison, histone modification, which is basically adding acetyl group to some of those proteins which wrap our DNA, that is the on switch. And that sort of happens like taking two sort of a reverse pole magnets and trying to put them together. They were sort of repel apart. And when they do, they open up the machinery for transcription into mRNA. And so generally DNA methylation is the biomarker that we're looking at. And the reason we look at this is because it is so robust. And so there are over 29 million spots in every cell where this can become methylated. And these really happen at places we call CPG islands. And these are basically cytosine phosphate guanines, where the methylation actually attaches to those cytosines. So that's actually what we're looking at whenever we're taking a sample here in our lab. Usually the samples that we take are from blood, and what we do is extract that blood, and then we sort of process it to find out how many of those locations in your DNA are methylated. And what we get there is actually a percentage. So we actually look at 900,000 locations, and at each location we get what we call a beta value, which is essentially just a percentage of methylation. And by looking at those patterns and using computer learning and artificial intelligence techniques, we can start to read the patterns of methylation and find certain locations which might be indicative of certain outcomes. So now there are a lot of ways to interpret this via algorithms, these basically mathematical formulas which can read this DNA and methylation to tell us a lot about the person. Right now, we can even tell you, for instance, how much you've smoked across an entire lifetime. We can tell, for instance, if you're going to respond to certain medications like metformin by having an HbA1c response, or if you're likely to develop side effects. We can actually even predict when you're going to die with this with fairly high degrees of accuracy, better than any other predictive death marker. And so the applications for this are incredibly robust. Not only can you predict phenotypes, for instance, things like schizophrenia, which were only once clinical diagnoses, you can actually see these markers in blood and now have an effective clinical diagnosis that is not based off of just I would say, clinical symptomology, but also blood-based biomarkers. So you can do a lot with this. You can even estimate protein levels. You can estimate metabolite levels. You can really cross-train almost anything to be predicted through this DNA methylation, which is why it's so powerful and so robust. However, as I mentioned, the primary application that we do at TruDiagnostics is to quantify the aging process and to use these markers to develop these epigenetic clocks, which can tell us a lot about how you're aging. And so whenever we usually introduce this concept, most people tend to be familiar with other types of biological age testing, particularly things like telomeres. And so whenever we sort of talk about telomeres, we like to always compare these two because telomeres have been around for a long time and they're absolutely correlated to age. Telomere length, I should say, is absolutely correlated to age. Generally, the older that we get, the shorter that our telomeres get because we undergo DNA replication and start to have some telomere attrition, losing the end parts of our DNA. But generally, in several review studies like the one you see on screen here, telomeres have been a little bit sort of lackluster in their ability to predict outcomes. And that's really what we're doing this for, right? We're really trying to gauge your aging so we can figure out what is most likely going to happen as a result of that aging. As we know, it's already the number one risk factor for most chronic diseases and death. And so this study sort of said, although telomere length is extensively validated, there have been multiple studies on this, it has really low predictive power and therefore misses out on what we really want to do. And so going back to these biological age clocks, these are incredibly predictive. And going back to some of those statistics we had earlier on the screen, if everyone in the world were to reverse their biological age by just 7 years, we'd be able to cut disease in half overnight. And so that's really what we're trying to do, is to get everyone taking this metric to quantify their aging and then taking the necessary steps to improve their aging rate and reduce it by at least 7 years so that we can reduce both morbidity and mortality. And so this is exactly how we believe biological age should be used. We think that it should be used as a preventive medicine biomarker, something that everyone should take to try and fix this end goal. And if we don't have you convinced yet, hopefully we will toward the end. But at first, these biological age predictors, particularly these epigenetic clocks, weren't actually used for medicine. They were used for really other interesting things. So for instance, they were used in forensic crime scene investigations to see how old someone was if they left their DNA at the crime scene. Secondarily, they were used to date refugees from the Syrian refugee crisis to see if they were adults or minors and therefore eligible for asylum in Europe. And so they were used in a lot of interesting ways, but really until a lot of data was created, they didn't start to see these links, which is that generally those people who were older than their biological age, or I should say their biological age was older than their chronological age, they were at significantly higher risk for negative outcomes. Well, whereas those people who were younger via this measurement than their chronological age, they were actually protected for risk of that outcome. And that's how we got to some of these major ties to disease, where we see that having a reversed epigenetic age is significantly protective of disease. I always like to use an example of cancer. Cancer is obviously a very scary outcome, but also age is the number one risk for almost every type of cancer. And so here you can actually see that from this same study that we mentioned in 2017, where for every 1 year that you're older biologically than chronologically, so if you were 53 years old and your biological age was 56, then you would essentially have an 18% increased risk of developing cancer and over a 40% risk 45% risk of dying of cancer in the next 5 years. And so even small increases in your biological age rate over your chronological age can mean massive increases in the risk of disease. And the beautiful thing about aging is because it's so important for every single disease, we can actually report on all of these diseases. We can take a look at your biological age, as you can see an example of one of our reports right here, where we can actually tell you the difference between your biological and chronological and what that means in terms of your outcome. We can tell you what that means for your cancer related death predictions, your metabolic syndrome, everything from ventricular hypertrophy to autoimmune diseases. We can show that this is affecting and therefore increasing and decreasing risk. And so this has a lot of utility because it is a factor that if you can reverse, it improves your outcomes in all of these different criteria. Everything from Parkinson's, Alzheimer's to osteoarthritis can be improved if you have a better epigenetic age. And so that's really our entire goal, is to treat the biggest risk factor for every disease in someone's life. And we do this through a sort of a suite of different types of reports. We have our true age report, which is the fundamental report we do, where we break down your biological age and talk about some of the things that are happening in your life or have happened in your life that might have influenced this in a positive or a negative way. We actually even break this down into two different types of aging called intrinsic and extrinsic age. One is essentially an immune age, where we're actually able to report things like your immune cell subsets, like how many percentage of CD4 cells or CD8 T cells do you have? And that is actually even expanding. And previously only able to be done via flow cytometry. Now with just one drop of blood, we can get as much information as a lot of really complex flow cytometry. And so in addition to that, although we are not huge fans of telomere length, we actually are able to output telomere length as well, all through this methylation-based diagnostic. And then our favorite, and the one I want to spend a little bit of time on today, is this idea of the pace of aging marker. So in addition to telling you what your overall age is, we can actually tell you right at this moment how fast are you aging. And this is an amazing algorithm which was created by research from Duke and Columbia, which has a lot of clinical utility and is one of our favorite, if not considered the best, scientific biomarker of aging. And so to go into that a little bit further, so to talk about all of its different benefits, I want to show a little bit of how it's output on our report. And so this actual rate of aging, again, it gives you a number between right around zero point 0.6 to 1.4. And this is how many biological years per year that you're aging. And you can see in this population level graph that it tends to go up across a lifetime. So our rate of aging tends to increase over the course of the lifetime, starting a little bit low, and this is our actual patient population. So you can actually compare where you're at to everyone that's taken our test in real time, and that's now over 15,000 patients, and we have the largest private epigenetic database in the world to create new algorithms. And so one of the things we should also mention is that this is Dunedin Pace of Aging is the first ever third generation algorithm. It is the most up to date. Just to give you a little bit of background here, this is a really important thing, but also can be a little bit complex. These first chronological age clocks, as I mentioned from 2013, were trained to predict an individual's chronologic age. And they were really powerful, still more predictive of aging outcomes than any other biomarker that had been created up until that point. But the problem was the better that these clocks got, the closer they got to predicting your birth date, which is something we could just easily ask for. And so that's not what we really want to measure here, right? Although those first biological age clocks were capturing a piece of biology, they're actually trained to predict chronologic age. And so these second generation clocks changed that, where instead of being able to predict the chronological age of a patient, they were trained to predict those biological phenotypes, right? Those things that we see happen with age, things like reduced muscle mass and increased frailty, things like worse immune systems, for instance, or changes in blood-based biomarkers. And then lastly, this third generation clock was the only clock to have done this over time. And that is really where this Dunedin pace marker is so helpful. It actually started in 1972 with a group of over 1,000 children who were 3 years of age. And what's happened is that this cohort has actually been tracked across their lifespans. So they started when they were age 3, and now they've been followed over 45 years, and we're actually having our 51-year age follow-up right now. And with this, we've been able to take a lot of biomarkers from them across their aging process, everything from cardiovascular and metabolic biomarkers to retinal imaging scans to dental imaging and even facial imaging, as we'll show a little bit further. And with this, we've been able to create this instantaneous pace of aging. So over the course of a lifetime, we've taken all of these different factors, everything from HbA1cs and lung spirometry metrics and gum health measurements and white blood cell counts and cholesterol to create this pace of aging, or how people age across a lifetime. And that's how we actually get this number. But we then train that pace of aging to be predicted via these epigenetic methylation biomarkers. And what we found is that this clock is incredibly informative. And so I want to go a little bit about some of the patterns that we've seen, as well as how this is actually used in clinical practice. And so, as I mentioned, we have been following this cohort, and every so often we check in with them to look at how this rate of aging is predictive of different types of outcomes. And so the data I'm going to show you here is from our 45-year follow-up study. So this is when we took all 1,000 people in the cohort whenever they were 45 years of age, and we performed a lot of different tests on them. And what you can see here is the pace of aging there on the x-axis versus their performance on these tests on the left. And as you can see, the faster the pace of aging, the worse the grip strength. This is also the same with things like balance. Generally, the faster the aging rate, the worse your balance was. We also see this, for instance, with things like cognitive decline. And so here you can actually see that the change in IQ from childhood to age 45, with those people who are aging at closer to a rate of 2 being on average 15 IQ points lower than those people who are aging at a rate of 1. And so we know this affects your balance. We know that it affects your grip strength. We know that it affects your brain and IQ. We also can actually see this in the brain with brain MRIs, where we can look at the cortical thickness of the brain and the surface area of the brain being diminished. And then everyone's favorite, we can also see this with facial aging. So the people that you actually see here in front of you are all the same chronological age. They're all age 45. However, the people on the left are the slowest aging members of the cohort with our testing versus the people on the right who are the fastest aging members of the cohort with our testing. And they look to be, 20 or 30 years apart in age because biologically, at least, they probably are, which brings this idea of phenotypic variation back up, right? Where we know that some people age really well and other people age worse, but now we can actually quantify it. We can quantify it with overall epigenetic clocks, but also paces of aging. How fast are you aging right at this moment? And so I also like to show these to patients because whenever people talk about biological age, a lot of people just talk about lifespan or how long someone is going to live. But in the case of this particular algorithm, we know that these things are inextricably linked, right? The rate of aging or how you're aging doesn't just affect how long you're going to live or how you're going to develop disease. It also affects all these quality of life related metrics. So it affects everything from how you move about the world to your ability to balance, to your ability to think, as well as even how you look. And so I always show this to patients and say, absolutely keep doing Botox, right? Try and treat the symptoms, but at the same time, you should probably focus on the underlying issue, what's causing you to age in appearance in the first place. And again, this was not just for these categories, but we had these for multiple categories, everything from, as I mentioned, gait speed to motor coordination, to perceptual reasoning, to even your self-rated health. How well do you feel? All of these had an impact with this biological age measurement. We're highly associated to this. And as a result, we think that this is why it's so important to take this measurement early and to try and improve it as much as possible, because with small improvements in this metric, you're improving your risk of every other disease outcome or aging outcome that you would want to avoid. And so just to put this again into some other analyses, we also looked at how the Newton pace clock was able to predict negative outcomes such as disease and death. And so here we actually use the Framingham Heart Study cohort as a way to do this. And here you can see there are three different lines. There on the top in the blue, you have the slow agers. And so versus those people who are fast agers or more than one standard deviation away from the average age. And then you also have those average agers here as well. And what we can see is that generally across 15 years, those people who were fast agers had over a 50% death rate. And we see that conversely, the people who were slow agers had less than a 10% death rate. So this plays a major, major impact on your ability for survival over the course of 15 years. And so this plays a major difference. The idea is you want to keep this definitively below 1. You want to age slower than 1 biological year per year. But in addition to that, we can also see how it reflects even against some of the previous epigenetic clocks in this area. So if any of you have taken some of these epigenetic clocks before, there are a couple things we always ask you to look out for. One is that we highly recommend that you're using a published clock. Otherwise, it's like going to a fortune teller. You can believe the results, but unless you have it, you can choose to believe the results, but unless you have proof, such as these validation cohorts, it can be really hard to trust. So make sure you're using both a published clock, but also then choose a clock that is high predictive value. So here you can see even some of those original clocks, like the Horvath clock from 2013 there at the top. And what we can see is that one standard deviation of Dunedin pace acceleration leads to a 64% increased risk of mortality versus one standard deviation on some of the original clocks, which are still being used, which leads to only a 2% sort of increased risk of mortality. And so this is definitively the best clock out there. It really outperforms every clock, not only in predicting things like mortality or disease like cardiovascular disease or stroke, but also in predicting quality of life. And so here on the bottom, you can even see those hazard ratio predictive values for things like any difficulty in reaching or standing or pushing large objects. All of these things, which again we would consider quality of life related metrics. So the big takeaway here is that the slower the aging, the better your life. Period. The more the less likely you are to develop disease, the less likely you are to die earlier, and generally the quality of life will be significantly increased. And so all those things I think are outcomes we all want, and that's why aging is such a big point of treatment. And we also know that, just to add some other statistics to this, our goal is to keep this rate of aging as much as we can below 1. And so even just being slightly above 1, so as 1.01 biological years per year, you'd actually increase your risk of death by 56% over the next 7 years and increase your risk of a chronic disease diagnosis by 54%. And then in addition to that, those people who are fast agers were on average 65% more likely to die than those who are at normal or slow aging. So keeping this as low as long as possible, is definitively something we want everyone to do. And one of the other things we should mention is that your aging rate actually starts really in early life. We've done a lot of sort of young adult studies, and even the cohort we had starting at age 3. And what we saw is that these behaviors that happen in life, everything from your socioeconomic class to the amount of polyvictimization that you have, can actually affect this rate of aging. And so this is something that starts early. Aging is no longer something that we start to consider happening in our 30s, 40s, or 50s. This is something that is happening from the moment we're born, in a process that we can actually improve across life. And so there's never a time too early to do this and start treating age as the primary outcome. And when we do, we can actually see some really good results. So for instance, one of the things that has been the most validated to change this marker is caloric restriction. Caloric restriction, sort of eating less calories than you are outputting per day, is one of the most well-validated interventions for longevity and health span. We know that across mammal species, caloric restriction tends to increase lifespan and decrease the amount of morbidity. And that's exactly what we see here as well. We actually use this Dunedin pace calculator in the calorie trial. And this was a 10% caloric restriction trial. So they were eating 10% less calories than they would intake, plus the amount that they were burning per day. And in that 10%, we actually saw reductions in the rates of aging just from a 10% calorie reduction. And here you can actually see the change in biological ages, with the change in the non-caloric restricted group being on average 2 years. And then secondarily to that, the people who were doing caloric restriction had significantly less aging over that time. And so these markers, in addition to being great biomarkers for prediction, are absolutely changeable. That's another great thing about methylation, is that unlike genetic testing, which you might take once in your life, these epigenetic factors can be influenced by everything. They can be influenced by diet, nutrition, and we'll talk a little bit more about that as well in some of the studies which have shown that definitively. And so with that being said, that is our rate of aging algorithm. It is really one of only 14 different outputs that we would have from this type of testing. But I think it goes to show you the importance of thinking about aging as a disease, as well as just how predictive some of these algorithms can be, and why epigenetic methylation is such a great platform for implementation and discussion in the future. And so the last thing I want to do is, I don't want to knock telomeres too badly, because we do output them on our tests. And I want to talk a little bit about what our output looks like. So our method of determining telomere length is based via DNA methylation. And unfortunately, as we mentioned, telomere length is not the most predictive algorithm, but our version of telomere length actually outperforms regular telomere length testing in predicting time to death, time to coronary heart disease, and congestive heart failure. So not only is it got double the correlation to age as regular telomere testing, it is also more predictive of most of these outcomes as well, which makes it hopefully a really good biomarker to also add. And it generally will look like this. We'll report out your total telomere length, as well as where you fit in the population and where your percentile score is. And this can be really indicative of things in certain processes like cellular senescence, for instance. As those cells become critically short with their telomere length, they generally want to go senescence, and that process can lead to a ton of inflammation and inflammaging, as we call it. And so getting telomere length is another process we'd like to add, because if you were to reset epigenetic clocks to 0, you would still see telomere length shortening. And if you were to make telomerase constantly active, you would still see epigenetic aging. So they're both parts of the aging process, but the one that is vastly more important are these epigenetic clocks, because they're much more significant to development of disease outcomes. A recent study looked at the difference in phenotypic aging among a cohort, and said right around 2.8% of the variance in the phenotypic aging that we have is due to telomeres, where right around 35% of that is due to these epigenetic clocks. And so we still output telomere length, but we would definitely prioritize those epigenetic clocks as the primary biomarker before you look at this one. And so, I think that this sort of tells you a lot about the tools in the toolkit if you were to do our testing to really quantify that aging process, and something that can really be done in everyone to improve how they're aging and what to expect as they get older. But with that being said, we also want to talk about methylation as a platform and what we can actually do to change it. And so what I want to do with a lot of my talk remaining, and this will go a little bit quickly, is to talk about some of the patterns and trends we've seen with epigenetic aging, and then how to really improve a lot of those as well. And so before I do that, I also want to go into sort of a famous experiment. This is called the Goody mouse experiment, and really was one of the first studies in epigenetics which really got people excited. And so what you're seeing here in front of you are actually two genetically identical mice. So they have the exact same DNA, but when they were pregnant, one of their mothers was fed a diet which was supplemented with choline, folic acid, and vitamin B12, and the other mouse did not. So what we can see here is this agouti gene, as a result of that nutritional sort of behaviors of their mothers, affected the phenotype of the offspring. And so the normal mouse had been supplemented with a lot of those methyl cofactors. And they were able to appropriately silence this agouti gene through methylation or DNA methylation, which turns that gene off. And vice versa, the agouti mouse was unable to do that because they didn't have the necessary cofactors and they weren't able to regulate their DNA expression. And as a result, they turned out to be a different color. They were blonde. And in addition to that, they had much more disease. So they were obese and they developed metabolic disease and diabetes as a result of this as well. And so this was one of the first studies to show that even people with the exact same DNA can have that massively different phenotype differences just through nutrition alone. And this was done by Randy Girdle at Duke, who is now working on it with a project on us on the imprintome. And it really brings up this idea that our methylation patterns in really our DNA is expressed as a result of the inputs that we give it as a system within our body. And these inputs can be everything from nutrition to pharmaceutical compounds to even psychological stressors. Everything that we do on a daily basis, the amount of sleep we get, the amount of stress we have, all impacts our epigenetic methylation. And so this really brings this idea of functional preventative medicine and why it's so important. Is because even though we might have the exact same DNA sequence, some of us might be more suited to age and others might be less suited to age based on this epigenetic expression. And so these things and these epigenetic markers are absolutely modifiable. And so that's really what we want to talk about toward the end of this is that sort of the hope in all of this, where we know that aging can now be quantified in a way that we've never really done it before. It has really high accuracy and is incredibly predictive. And so now that we have these great biomarkers, what can we do about it? What can we do to change it? And this is still a relatively new part of this investigation. You know, these clocks only came out in 2013. The first ever interventional trial came out in September of 2019. And then shortly after that, we had the pandemic. So a lot of research was unfortunately unable to continue. And so we don't have a lot of studies here on how to reverse these things, but we do have a lot of data from meta-analyses. And so that's really what we want to go forward with now, is talking about what we know from really large cohorts. And so to really start this discussion, I always like to bring up a paper that was done by some of our other collaborators at Yale, particularly Morgan Levine and Albert Higgins Chin. They really took 156 published papers that reported factors on epigenetic aging to see where their common associations were across the many clocks. Unfortunately, Goody pace was not included in this because it's a little bit more recent and up to date. But with that being said, we can see a lot of really good trends. And so what we see here are some of the major associations for each algorithm. Generally, the larger the circle, the more of an impact it plays. And so what we see here are things that make a lot of sense. This is probably not going to be groundbreaking. It's pretty intuitive for everyone. But we know things like, for instance, alcohol use or low socioeconomic status or low education level, poor lung function, depression, smoking. All of these things play a negative impact on these epigenetic clocks, which I think makes a lot of sense. But we also see some other things like metabolic syndrome, particular matter or pollution exposure, PTSD, all having effects on these different markers, which tells us a lot about what we should do epidemiologically. We also know, though, and some of the interesting things we've also found are the degrees or the power that actually these things have in reversing these outcomes. And so, for instance, we know that smoking plays a major impact. We know that BMI and sort of obesity play a major impact. But we actually see that physical activity might not have actually as big of an impact as we would have thought. A lot of people talk about physical activity as being one of the most important things, and it might be so in its ability to reduce some other diseases, but not necessarily as one of the major movers of aging. But we also see all the diseases which are highly associated with this, everything from cancer to COPD, cardiovascular disease, diabetes, and overall death, right? All the things, the major causes of death and the major causes of mortality are all highly related to this measurement. And so whenever we're talking about things and behaviors, there are a lot of things we can recommend immediately. Number one of which is stop smoking, for instance, which again, if you're not already doing that, I'd be surprised, but this might be able to give you an objective way to track that patient's behavior, because we can actually tell you if you're a current, former, or never smoker. And we can actually even tell you and estimate how many pack years you've smoked across an entire lifetime. And so this can, in addition to helping you try and improve that behavior, it might also be an objective way to help your patient stay consistent with that behavior. And here we actually can see that these smoking scores actually are better than self-reported smoking at predicting outcomes, meaning that they're incredibly sensitive and again, they can be changed over time. One of the other big things, surprisingly, I think, is the impact of stress and lifestyle on a lot of these measurements. This is actually one of the biggest changes. One of the things I was most skeptical about originally. I was not a big fan of meditation because I was always thinking to myself, am I doing this right? Is this really meditation? But generally, people who are doing mindfulness, meditation, anything to reduce stress can have vastly improved epigenetic ages. And so I know this takes it a little bit out of the clinic, but there are things that you can recommend. Here you can even see the effect of cumulative lifetime stress on aging. And this has been replicated in many, many other trials, mostly thought to be linked toward aging through glucocorticoid related signaling and cortisol. But we also see that even things like your work engagement, your job security, your job strain, all play an impact into your rate of aging. And here you can see differences of over 1.5 years in some of these markers for anyone who works over 40 hours a week, for instance. And so this is, again, a way that we can connect everything that's happening into our body to this rate of aging, and then also that rate of aging to every risk of disease. We can also see that people who handle their emotions better, for instance, tend to do a lot better on this metric. You can see here that emotional regulation, self-control, and are all factors which can predict increases or decreases in this rate of aging. So again, as being someone who's very molecular based, scientific based, and interventional based, some of the best interventions that we've seen tend to be things like reducing stress, more of these considerations and lifestyle experiences. We also know that alcohol, before I go to there, I'll talk about again, even just relaxation treatment, post myocardial infarction had a major impact on reducing these epigenetic ages, some by multiple years. And again, we only have to get a few years to see really great benefit, because again, at 7 years younger biologically, everyone would reduce their risk of morbidity and mortality by 50%. So even just a few years can be a massive thing. And if we can get that just through relaxation and mindfulness exercises, that's a really good start. And beyond that, I also want to talk about alcohol. Generally, people who use alcohol more frequently have much higher risk of being at advanced age. On average, 2.22 years of age acceleration for those people who have alcohol use disorders. And this is another thing that we can actually track via their methylation patterns. We can actually tell you how much they're drinking, which previously has not really been able to be done. And so we can actually tell you how many drinks per week they're most likely consuming. Another way to keep your patients a little bit honest, and maybe even yourself. And then beyond that, we know things like sleep play a major impact. Those people who had irregular sleep patterns could, on average, be around 4.13 years older. And establishing effective sleep patterns could reduce epigenetic age by 2.4 years. And so again, these are major differences, multi-year age swings, which can happen from just implementation of better lifestyle, nutrition, and other factors in our daily life. And again, here you can see it again, where insomnia symptoms, the more types of insomnia symptoms you have, the worse your epigenetic aging. And we can go on this for a long time. As I mentioned here, physical activity has a much smaller effect. In fact, those who participated in sort of aerobic and anaerobic activity over long periods of time only had on average 4.41 years of lower epigenetic age, meaning that the physical activity surprisingly doesn't play a big of a role into our biological aging process as maybe some of those other categories. But nutrition is a huge category, and one that we could talk a lot about. Again, what we see here are that certain types of foods or consumptions actually change different parts of aging. So our immune system might be more connected to the fruits and vegetables that we eat, or the amount of exercise that we do, and maybe chicken consumption, for instance, is better at reversing that baseline pure epigenetic age. We also see that diet quality significantly matters. Here you can see the sort of scoring on this DASH style diet, generally, which means higher intake of vegetables, fruits, nuts, and whole grains, and low-fat dairy tend to be better for the aging process. You can see some of those changes as associated with them, which are highly significant. All of them being, below these significant p-values, which is great. And so again, we know that diet quality is incredibly important to aging. We can also see this even with certain types of supplement related things like carotenoids, where those people who are eating more carotenoids are going to be generally at a lower age. So supplementing with things like carrots is not a bad idea. We also know that things like the Mediterranean diet tend to be positive, which again backs up what we know from other research, which is phenomenal, because this is showing us a consistency among things. And if there's one way to really wrap up that diet section, it is to reiterate what we spoke about earlier, which is the impact of caloric restriction. Caloric restriction is a great way to reduce almost every one of these biological age clocks. So in addition to hopefully improving that diet quality, just reducing your caloric intake can have a major difference. And so the pace of aging is reduced by 0.41 years per one chronological year after reducing caloric intake by just 11%. And so this is one of the treatments we recommend for everybody. And already, I think you can see some of these patterns we would suggest. Doing things like caloric restriction, having better diet quality, improving your sleep, all the things you're probably doing already. And with that being said, there are a lot of really exciting interventions coming forward to really reverse these metrics. And we won't talk about them today on the call, but there are a lot of things that are just mind-blowing that are coming in the future. Things like cellular reprogramming, where they can actually take some growth factors like these Yamanaka factors and actually reset the age of these cells to 0. And in doing so in several experiments with Dr. Sinclair at Harvard, they've actually been able to do this in blind mice to restore vision, for instance. And so these things that are changing phenotypes in ways that we never really anticipated before. And these are all currently happening. But right now, the biomarker is just being created and it is absolutely ready for use. You can certainly use it in your clinic. And we'll talk about, again, just to sort of finalize this up, we'll go through really, really quickly some of the supplemental things that we know to change these markers and talk about how you might be able to add those as well. One of those, as we talked about, even with the mice study, the Goody mouse experiment, we know that methylation cofactors and the interplay between some things like COMT genes or MTHFR genes can play a major impact. So we know that, for instance, women with the MTHFR 677CC genotype tend to be at accelerated aging compared to those who do not. But we also know that this is relatively easily fixed by just supplementing with folic acid, B12, or 5-methylfolate. When doing so, we actually could see relative quickly reductions of those epigenetic ages as well. Unfortunately, we also know that men who have MTHFR 677CC variant do also have faster aging, but it was not fixed by that methyl group supplementation. And so we're still working on ways to improve that. In addition to that, we've seen some other clinical trials. This was the first ever interventional trial which was published. And this actually only had a small number of participants. It was done at UCLA and used metformin, growth hormone, and DHEA as a way to reverse the aging process, mainly through trying to encourage thymus regeneration with growth hormone. And although growth hormone can be very, very powerful, it also sometimes can increase insulin's resistance. And so as a result, that's why DHEA and metformin were given to help prevent that side effect. And whenever they did this, they actually did this over the course of a little over a year and a half. And they saw a lot of different improvements, a lot of phenotypic improvements, like reductions in PSA, improved kidney filtration rates, and more thymic MRI density. So they showed that they probably improved the thymic involution, and that meant that they probably had a higher NAD to NADH ratio, and epigenetic age was actually decreased by, on average, 1.5 years over the course of 18 months. So this was the first ever interventional trial that actually showed this reversal and was a major, major impact to the field. I think that generally we see some really good impacts in our larger data set with DHEA, but probably not as much so for growth hormone or metformin, but hopefully that will change. We also know that vitamin D is great to supplement with as well. Even just a 4,000 or 3,000 IU of vitamin D daily can decrease epigenetic age by over 1.85 years in just 6 months. And so this can also play a major difference. We also have many other studies to back up this particular claim about vitamin D, where in some studies, longer term implementation of vitamin D was able to reverse epigenetic age by around 0.25 years and increase telomere length. And then also we have some other things coming up in the future where we're looking at things like menopause and replacing hormones as it relates to menopause, which we know that menopause drastically accelerates biological aging. And actually one of the very few times that women don't age better than men. Men generally have worse aging across the board, and is one of, generally a bigger risk factor is actually male sex. We also know that lithium actually shows some positive effects. Those people who have been taking lithium for bipolar disorder on average have lower epigenetic ages. And so low dose lithium might be another reason that we can sort of start to implement these protocols and see change. And right now now we're investigating everything from stem cells to exosomes, to bariatric surgery, to hormone replacement, to NAD, to senolytics. We've got data on almost all of them now, and so know a lot more about how to reverse these. And so this was just a quick way to review some of that data. But what we're really trying to do at TruDiagnostics is not only to give everyone the tools to control their own aging process, but to more than that, learn how to read that methylation patterns in our DNA. We always say that we're trying to create the Rosetta Stone of methylation biomarkers so that we can really read all of those different data points in many different cells and have one test that replaces many. Here are things we can already do with just one test. We can read out your history of exposures for things like heavy metals or smoking or drinking, as we already mentioned. We can even estimate over 150 proteins right now, everything from your C-reactive protein to IL-6 to your serum albumin, or leptin, or a lot of these proteins we can actually estimate with just one drop of blood. Very soon we'll actually have a predictor of senolytic cells, so we can actually tell you what your senescence burden is, and we can even diagnose those phenotypes too, right? What is your grip strength? What is your VO2 max? And what is your history of viral infections, for instance? And so this is really where we see the future going. We think that that epigenetic methylation will be a biomarker that everyone uses in the future for a wide variety of medical conditions, and are really trying to create the ways to read that data. And so hopefully that you'll consider using this testing, especially if you're doing any age-related testing. The idea that most people will use here is that they'll implement this into their clinic, doing testing maybe once or twice per year. We really don't recommend our full test more than every 6 months in order to make sure it's accurate and giving you the best age-related information. But most people would then, test their patients, implement protocols, and see if they can reverse or slow that aging process. Unfortunately, aging is still something we've not conquered. We're not yet immortal. I think that might change, over the course of the next few decades, with some really exciting innovations for aging that are coming down the pipeline, and millions of dollars are being invested every day into this research. So hopefully one day we'll be able to change it. But for right now, this is a way to quantify that risk and to find out what works for your patients or yourself on an individual level. And by addressing these biomarkers, you can certainly expect better lifestyle and disease risk across a lifetime. So with that being said, I hope this was a great introduction to this biological aging topic. We have many other reports which we could go into, everything from the number of stem cell divisions that you have to your ability to lose weight with caloric restriction can all be predicted through our reporting. So if you have any questions or would ever like to talk more, you can always reach out to us at support@trudiagnostic.com or Ryan@trudiagnostic.com, and we'd love to answer your questions. And with that being said, I'd love to answer any questions which might be happening or from the call right now, and then open it back up to Chris to talk a little bit more about the platform.
Yes, so that was fascinating. So we'd like to open it up. If anyone has any questions, please submit them through the questions field, and then I will ask them of Ryan, and then get you your answers. And if you need to think about it, you can submit them to info@avexiadiagnostics.com as well, and we will get you your answers as soon as possible. Let's just see. I know that. Let's see. Let's give it a second. Any questions? Okay. Yep. Mark Lamentia has a question. I have a population of scoliosis patients who I think this may be useful for. Have you had any studies with progressive scoliosis?
So unfortunately, we haven't, and I'd have to look up sort of scoliosis, and we have actually done a lot of sort of surgery-related investigations. We worked actually with University of California, San Francisco, to look at actually spine surgeries before and after. So we might actually have a larger data set of those with scoliosis. There's a little bit of work in scleroderma as well, but unfortunately, I would say that this is so new that a lot of those cohorts haven't been adequately built out. But we do know that aging impacts all of those risk factors. And so it might help to slow the progression. But if you start to build those unique data sets, you can actually even find a lot of other things in and of itself. If you do a lot in a particular condition, for instance, you might be able to find patterns which predict outcome. And not only I think could that be useful for the clinic, but also might be a valuable clinical tool for others as well. So if anyone is ever working with unique patient groups and would like to do any of those studies, we would love to do so. I'd love to talk a little bit further to see how we can sort of collaborate and find some interesting information. But we do know from that study that we did with University of California, San Francisco, that the aging rate actually predicts performance in surgery as well. It's actually a better predictor than frailty-related markers for surgery outcome or surgery complications. And so particularly with spine surgeries, this can be also a good factor to look at.
So I think you may have answered the question, but the follow-up was, did the surgeries reduce aging? So I think maybe you touched on that, but feel free
Yeah.
to add.
Well, so I should say the surgeries themselves, we didn't measure after surgery. And so we do know that surgery or any type of invasive procedure like that will actually have a transient rise in biological age. So for a few months, things that are really stressful on the biological system can cause those increases. For instance, things like pregnancy or surgery are two really good examples. But in the case of what we did in that particular study, we actually showed that we could predict surgery outcomes, how likely they were to have a positive surgery outcome, how likely they were to have a fast recovery through their rates of aging. So we actually would be able to predict that better than telomere length or any other biomarker that they were traditionally taking. And so we hope to do a little bit more in surgeries as well to be able to predict outcomes, but we don't know necessarily if the corrective surgery was able to improve biological age.
Okay, great. Another question from Mylan Gagnon. Um, Comment, really complex and interesting. Do you help interpreting the results? Now, just quickly before Ryan jumps in there, we offer interpretation through Dr. Wayne Sedano in the Ask the Doctor feature, which I will talk about in a second. But we always will consult with Ryan and TruDiagnostic to get you any support that you need. Anyway, Ryan, with that, you can jump in there.
Yeah, certainly, and we definitely will always I would say work with the Vexia's team to make this available. But I will also mention we do a lot of one-on-ones to help with training. The each of these algorithms can be slightly different, and which makes this relatively complex because the lessons and the takeaways from each of these different reports might be slightly nuanced. And so, with that being said, we always do education to try and to help talk about some of those nuances, and we'll continue to do more as our platform is built out. One of the things I didn't mention as well is that we're measuring right around 900,000 different locations on the genome, but for a lot of our reporting, we're still using less than 100,000 locations, so not even 1/10 of really where we could be. And so over the years, as this data continues to increase and the people you sort of have more algorithms to read this data, we'll continue to update results in perpetuity. So if we find out more insights, we'll actually release new reporting. And so we actually have new reports come out around every 6 to 8 weeks. Our next report will be sort of a protein and an inflammation report. Then we'll have one that's able to predict your VO2 max, your grip strength, and your walking speed, some of those other phenotypic markers that are associated with aging. And so those will be added even just over the course of the next few weeks. And so anytime that those are updated, we also do education on how to review those reports and to use that data as well.
Okay, so I think we're going to proceed on. Let's see here. Ryan, would you mind just proceeding to the next slide? Great. So we have the Ask the Doctor feature, as I mentioned. It's a free service available to all of Vexia clients. Dr. Wayne Sedano, our Director of Clinical Support and Education, will review results, interpret results, go over test recommendations. It's free. It's he will get back to you within 24 hours, if not shorter. And at the same time, we do offer a video conference option for a slightly a slight fee. But you can find that when you go log into your Vexi account. Along the left side, you'll have a quick link to Ask the Doctor. When you get to that page, you'll see the two options, and you can make an appointment, and you can see pricing as well. So let's see here. Okay, so now that we've learned so much about epigenetic methylation and biological age testing, I would like to review how to order the testing before we conclude the webinar. So as you can see from this slide, first you'll need to log into your Avexia account and go to the Avexia link ordering banner, which is located on the left-hand column of the dashboard. You will then need to create a patient or assign the test to a patient, then select specialty labs and go to the TruDiagnostic tab. Locate the available test that you want for your patient, and finally, to complete the order, click on the green place order button. About learning about Avexia Diagnostics or contacting us. For any questions or issues you may have, contact Avexia Diagnostics by email at info@avexiadiagnostics.com or by phone. 5 days a week at extended hours, 8 a.m. to 8 p.m. Eastern Time at 888-852-2723. A recording of this webinar will be available by email in the next few days. Let's see. And I'd just like to thank Ryan for this informative presentation. Thank you again all for joining us on this webinar event. Until next time, from everyone at Avexia Diagnostics and TruDiagnostic, stay healthy, stay safe, and we wish you all the best on your pathway to wellness. Thank you so much. Have a good evening.